watching the video of the tongue going up in the back and dropping it was very instructive. That was great. Because then I just played around with it, right? So, and I don't know if this is bending or not because I'm not there, but then when you play with the volume, you change the sound.
You're changing the tone, yeah. Go ahead. It's good you bring that up because
What is that?
It is not bending. Bending is the
Okay.
changing of pitch.
Okay.
You are moving your mouth, your tongue, to create a smaller cavity than a larger cavity, so you're changing the tone.
Okay.
But that early exploration is good because you can tell okay, that sounds thin and that sounds deep and resonant. We want deep and resonant.
So it's really the same notes.
Yes.
You're just changing the tone.
You got it.
Okay.
Yeah.
Okay.
And you'll probably...
I don't have an ear for that, so I'm learning.
You're developing, yeah. So do it again and fill up your mouth with the tongue to get a really thin, tiny tone. So that's wimpy, whiny tone. Yeah, as soon as you opened up your gullet, became like a frog, everything came open.
Yeah, okay.
Yeah, and that's good practice to do. You just got to do it in a nice, quiet room. And you may want to do that on your G harmonica. I mean, the A's in the lower keys of harmonicas, but the G's even one key lower, and you can even hear that more.
Right.
Would you like to know why the tone sounds different?
Yeah.
Okay. So
yeah, because I'm a technical
I
guy.
knew you would like this. Yeah. For
mechanical kind of.
For the student, if you like the idea of a little bit of science, continue on. Otherwise, go to the next video. When you pluck a string. So the upright bass behind me. There's a bridge and there's the nut where it's affixed at the top.
Right.
You pluck that string and it's vibrating from both stopped points.
Okay.
That note, let's just call that note C.
Okay.
That note is vibrating from end to end, and that's the fundamental pitch. That's what you hear the most.
Okay.
It is also vibrating at half its length.
Got it. Okay.
And that is 1 octave higher. Now, you hear that pitch as well, but it's just a lot quieter than the fundamental.
Okay.
If we were to take I don't know if it's not an oscilloscope, it would be what's the flashing light that you can change the speed of?
Strobe light?
Strobe light, thank you.
Right.
If you set the strobe light, if that was...
To the frequency, you can actually see the string in that.
Exactly, yeah.
Cool.
So if this fundamental frequency was that 220 we were talking about on the one blow read on your A harmonica, if you set that to 440, you will see the string vibrating.
You'd see the different curve.
Yeah. It would look just like this.
Like held in position.
Exactly.
Yeah.
And the little point right there where it intersects is called the node.
The node, yeah.
And you hear that.
That is not moving, that's the node, yeah.
Yeah. Got it. It is in its entire length, but it's also moving it.
Right.
Yeah.
Yeah.
It is also vibrating at 1/3 of its length, which is a fifth above that original C. Actually, it's an octave and a fifth, but we get the note G.
Okay. So a fifth is?
A ratio of 3 to 2. You've
got
got
it. Okay,
three vibrations, yeah.
Okay, got it.
Then it is vibrating at 1/4 of its length, which is actually a fourth above the G. That's just coincidence. So we get C again. Then it's vibrating at 1/5 of its length. We get E. And then 1/6, we get G again. We continue, we get somewhere between A and B flat, and then C again, then we get D, and then it starts getting really, really close together. So all of these notes.
All at the same time?
All at the same time.
Wow.
So we have C, C, G, C, E, G, et cetera, et cetera.
Just out of the one string?
Out of the one string, yeah. And that's what we can call, there's multiple terms. You'll hear it called as the partial series. Sometimes you'll hear it called the overtones, or the overtone series, or the harmonic series.
Okay.
But just think of it as notes that are sounding above the fundamental pitch. And that's what tone is.
And of course, it's only above. It can't be below because it can't vibrate any slower than the fundamental pitch.
Exactly.
Is that the deal? Okay.
Yes, yes. And subharmonics are only caused through electronics.
Okay.
Yeah. So the amplifiers and effects pedals will do things to help get you lower than you physically can get.
So why is the fundamental pitch the one you hear the most, though? Why is
probably it's just moving the most air.
Okay.
Yeah, the amplitude of that is the loudest.
So the same thing is happening. So we're talking about a string. Mm-hmm. So that's happening on the reed?
Yes.
Okay.
Well, actually, it's the reed that is. The reed is sending those puffs of air out, So the reed is creating the mechanism for those puffs, those waves,
Right.
to hit your ears.
Oh, got it. Okay.
220 waves
Right.
that are hitting your ear in 1 second.
Got it.
It is your cavity that creates the tone. So if your mouth is small, what's happening, because your cavity, your resonant cavity, is smaller than the size of this fundamental pitch wants it to be, it will be reduced in volume. So let's say that your cavity is really big and open. At a certain point, your cavity is going to be the same size as that pitch. Let me make something a little simpler. If I get a block of wood and I strike it,
Right.
let's say you hollow out the center so you get a little bit of resonance going, you're going to hear a pitch. If I make that wood block smaller, the pitch is going to be higher.
Right.
So let's say the volume of that block, as it gets smaller, the pitch goes higher.
Right.
As the volume of the block gets larger, it goes lower in pitch. Your body,
Right.
that the larger it is, the lower the frequency. When the reed is vibrating, if your mouth cavity is the same size of that reed, you will get the fundamental at 100% of its volume.
Okay.
If your cavity is smaller than the fundamental, then what's happening is you're getting less and less and less of the fundamental sounding.
Okay.
So what happens when your tongue is in a place, your whole architecture is in a place where it is at least as large as your fundamental, because you can go larger than that actually, but you're not going to gain anything.
Okay.
But let's just say, let's get as big as we can, so
Right.
we're not going to chance it. Then you're going to have the deepest, warmest, roundest sound you can possibly get.
Okay.
Now, as your mouth gets smaller and smaller, as you were just doing, the reason why it started to sound thinner and whinier is because you are actually suppressing the lower frequencies.
So you start to hear more of the upper ones.
Exactly. So if we
okay.
think about this as size, you've got the lower frequency, you're getting all of it here.
Right.
And as you get smaller, it's focusing more and more on the higher frequencies because your mouth cavity is not large enough to allow those lower frequencies to resonate.
Got it.
So we're really talking about the resonant chamber of your mouth. So you really need to think about the reed as being the string on your upright bass and your mouth being the body of the upright bass.
Got it. Okay.
Next time you go to a local music store, strum a guitar with a standard size body. Then go into the ukulele and mandolin section, and they usually have a guitar that has a small body they call a backpacker. Like Martin has a guitar called a backpacker.
Okay.
It has a standard neck with standard string length.
Just a real small.
Strum that. That's the difference between your tongue being here and closing everything out, and the difference of it being back here.
Okay.
So here's the neat thing. That's also why when you play your one blow, and I play my one blow, we sound a little different. Because the way the architecture of my mouth is, and the architecture of your mouth, basically where your tongue
Right.
is going to amplify certain partials and suppress certain partials.
Okay.
And that is why when I play A, 220 hertz on a clarinet, and you play A on your harmonica, and the piano player plays A, even though it is the same frequency, they sound different because of the mechanism we're using to create sound. Because of the woods, for example, if we have
Sure.
a guitar, one's made with koa, one's made with spruce.
Right.
The woods, the thickness of the woods, the thickness of the bracing, the largeness of the body, the thickness of the strings, even though they look like generally the similar guitars, they'll sound different because of the woods, the thicknesses, the resonant and everything. They will suppress and amplify certain partials.
Okay.
When you watch the making of the V-Rod, they actually go in I want to say hyperbolic chamber. It's not hyperbolic. Is it hyperbolic? It's a chamber where there's no echo. They have all foam in the room.
Okay.
And then, so there is no echo able to happen. There's no reflective surfaces.
Okay.
Everything is dampened. You go in the room and it just sounds crazy strange. They have one up at Stanford.
Really?
And they'll have microphones in the room. So they bring in the V-Rod and they turn it on and they take a spectral analysis. 10%, 42%, 17%, 29%. They're taking a spectral analysis of the frequencies of that motorcycle. Then they'll take a hog, that they consider to be like the quintessential hog sound.
Right.
And they put that analysis right next to it. And the guy says, okay, we need to enlarge the pipes by about 1/4 inch, lengthen the pipes by about 1
In
foot
order to get the sound right.
to get the sound, the signature sound. And they'll tune the engine and everything until it sounds like the hog that we know of as, Harley Davidson motorcycle. And they'll do the same thing with violins. So if they're like, okay, we got this new line of violins, we want to make it sound better. And they
Right.
take a spectral analysis like, oh wow, that mid-range compared to the Stradivarius that they
Right.
played a moment ago, that mid-range is really weak. So they'll get out the wood carving tools and
Right.
they'll work more on shaping the top plate and the bottom plate, or they might lighten some of the bracing or whatever they may do,
Right.
and experiment until they get something that's voiced more similar to what they want to do.
Huh. Interesting. And you use the term voiced. That's exactly what we're doing.
Yeah.
We're voicing.
Yeah. So
Yeah.
you can think about the reed as being your vocal folds.
Okay.
And that's also why, for example, when you have a cold, you sound so thin because your resonant chamber is now closed.
Huh.
So we have 2 resonant chambers here
Right.
and our sinuses.
Right.
So as you close off the sinuses, we no longer have as deep of a tone because I've taken that out of the
Right.
equation. That doesn't affect us for harmonica playing because obviously we want to have that area closed. But whenever I say, Hob, your tone's a little bit whiny, then you need to think about, where do I take my tongue?
You sound like my wife.
Yeah. I hope, Rebecca, you're not watching this. So that's what creates good tone. And that's why those pictures on the wall, they have a large embouchure is the term that we use, a large
Okay.
embouchure. Always remember the tongue has the most effect on what we do on the harmonica, on
Okay.
almost any subject that we talk about. So that's why getting used to
Right.
how to manipulate that tongue in the back, which we've never had to do besides just speech.
Right.
Now, if you can mimic somebody, like someone who's really good at impersonator,
Right.
they've learned how to
They've-
shape
Right.
that tone. So, anyways, that's what makes the difference between tone is that we have a suppressing and amplifying of certain partials. And for you as a harmonica player, what creates a thin, whiny tone is a small chamber. What creates a big resonant tone is a big chamber.
Okay.
Your lower keyed harmonicas,
Like the G.
that's a low C.
Okay.
So I'm now a very small chamber.
Right.
You can hear those lower
Right.
frequencies much better. So that time you spent breathing on the harmonica can be good.
Okay.
All right, back to our regular programming.